Imagine building the fastest plane of its time. It's only to realize that the world beneath it wasn't ready. Not the skies, not the pilots, but the ground itself. The runways cracked, the tires exploded, the brakes caught fire. This wasn't a failure of aerodynamics or engines. This was something far stranger. A plane so extreme, so fast, that normal airports simply couldn't handle it. Today, you're about to hear the story of the aircraft that was too fast for the sky, but too fast for its own airport. When people talk about aviation limits, they usually imagine the sound barrier, fuel range, or pilot endurance. But there's a hidden constraint almost no one thinks about until it's too late. The moment the wheels touch the ground. Because landing a high-performance aircraft isn't just about slowing down. It's about transferring enormous energy into tires, brakes, and concrete in just a few seconds. And sometimes that energy is more than Earth's infrastructure can survive. This story begins during the Cold War, when speed wasn't a luxury, it was survival. Military planners believed that the fastest aircraft would always win, because nothing could shoot down what it couldn't catch. Engineers were told to push limits, ignore comfort, and forget conventional rules, and they did. They created aircraft that could outrun missiles, climb faster than radar could track, and cruise at speeds that melted metal. But in their obsession with speed, they overlooked one quiet detail. Airports were designed for airplanes, not rockets with wheels. One of the most infamous examples came from an aircraft that landed faster than most planes could take off. When it approached the runway, it wasn't gently floating down like a passenger jet. It was hurtling toward the ground with the kinetic energy of a small meteor. The moment its tires touched the runway, everything became a race against physics. Heat built instantly. Rubber softened, brakes screamed under stress, and concrete surfaces began to fail. Tires were one of the first victims. At extreme landing speeds, aircraft tires don't just roll. They experience violent acceleration from 0 to hundreds of miles per hour in a fraction of a second. That sudden spin-up generates heat so intense that standard rubber compounds simply can't survive. Engineers had to invent special tires filled with nitrogen instead of air, because oxygen would ignite under the temperature spike. Even then, blowouts were common. Debris would scatter across the runway like shrapnel, threatening engines and control surfaces. Brakes were even worse. The faster an aircraft lands, the more energy the brakes must absorb. That energy doesn't disappear. It becomes heat. On some experimental aircraft, brakes would glow white-hot after landing. In several cases, crews were ordered not to park near buildings because the residual heat could start fires. Some planes required special cooling crews to spray water or wait hours before maintenance teams could even approach. But the real shock came when runways themselves started failing. Standard concrete wasn't designed for repeated impacts at extreme speeds. Microfractures formed. Surface layers peeled away. In some cases, entire sections of runway had to be rebuilt after just a handful of landings. Military bases discovered that they could operate these aircraft in the air, but not on the ground. If you're enjoying this deep dive into hidden engineering limits, take a second to like the video and subscribe to Forbidden Engineering. It helps the channel grow, and it tells the algorithm you want more stories like this. Stories about machines that pushed reality too far. One aircraft in particular forced engineers to confront an uncomfortable truth. Even though it was technically operational, every landing damaged something. Tires had to be replaced constantly. Brakes wore out at insane rates, and runways needed reinforcement just to survive. The aircraft wasn't broken. The world around it was. It's created a strange paradox. The plane was one of the most advanced machines ever built. It could fly higher, faster, and farther than almost anything else in the sky. Yet it was chained to a tiny number of specially prepared bases. If it had to divert to a normal airport in an emergency, the results could be catastrophic. In some cases, diversion wasn't even allowed. The plane was too dangerous to land anywhere else. Engineers tried everything. Longer runways, special concrete mixtures, arresting systems similar to aircraft carriers, even new landing techniques designed to bleed off speed earlier. But each solution added weight, cost, and complexity. Speed had solved one problem and created 10 more. By the late stages of testing, it became clear that the aircraft wasn't just demanding new pilots or new maintenance routines. It was demanding a new planet built around it. And that's when decision-makers began asking a dangerous question. If an aircraft only works when everything else changes, does it really work at all?
Engineering once again crossed a line it couldn't uncross. The deeper engineers investigated the problem, the more uncomfortable the answers became. Speed wasn't just stressing tires and brakes. It was reshaping the entire concept of what an airport needed to be. Taxiways had to be reinforced. Turning radii had to increase, because the landing gear wasn't designed for tight turns. Even ground crews needed new procedures because approaching the aircraft too soon could be fatal. One of the most ironic discoveries was that the faster the aircraft became, the more fragile its operations grew. In the air, it was nearly untouchable. On the ground, it was vulnerable, dangerous, and expensive. Every landing was a calculated risk. Every takeoff required perfect conditions, and weather became a silent enemy. Wet runways reduced braking effectiveness. Crosswinds increased tire stress. A single miscalculation could destroy millions of dollars in seconds. This is where comparisons to aircraft like Concorde and the XB-70 naturally arise. Concorde needed specially reinforced runways and suffered tire failures that caused real disasters. The XB-70, though mostly remembered for its speed and beauty, faced similar ground handling challenges. These aircraft didn't just challenge physics in the air, they exposed how conservative and fragile Earth-based infrastructure really was. In many ways, airports had been frozen in time. They evolved slowly, built around predictable commercial aircraft with known limits. Suddenly engineers introduced machines that ignored those limits completely. The mismatch was inevitable, and it forced military planners to rethink strategy itself. What good is a high-speed aircraft if it can only operate from a handful of locations? What happens when those locations are compromised? The final verdict wasn't that the aircraft was a failure. Far from it. It proved what was possible. It expanded engineering knowledge. It influenced materials, science, braking systems, and runway design for decades to come. But it also delivered a hard lesson. Performance without infrastructure is illusion. Speed without support becomes a liability. Eventually, compromises were made. Operational limits were imposed. Landing speeds were reduced, where possible. Missions were carefully planned to avoid unnecessary landings. The aircraft continued to fly, but always under the shadow of its own extremes. It was no longer just fighting enemy defenses. It was fighting gravity, heat, and concrete. And this story isn't just about one aircraft. It's about a recurring pattern in engineering history. Again and again, humans build machines that exceed the systems meant to support them. Trains that outpace rail networks. Ships too large for ports. Power plants too powerful for local grids. An aircraft too fast for their own airports. That's why stories like this belong on Forbidden Engineering. They reveal the hidden failures behind incredible achievements. Not failures of intelligence, but failures of balance. Because true engineering success isn't just about going faster or higher. It's about integrating with reality. As you think about this aircraft, remember that the sky wasn't the problem. The ground was. And sometimes, the hardest part of innovation isn't breaking limits. It's realizing which limits you shouldn't break at all. If this story made you see aviation differently, let me know in the comments. I want to hear which extreme aircraft you think pushed engineering too far. And if you found this fascinating, share it with someone who loves aviation, military tech, or hidden engineering stories. That one share helps more than you realize. This was Forbidden Engineering, uncovering the machines that challenge the world itself. And if you stay curious, there are many more secrets waiting just beyond the runway. And when you really think about it, this aircraft didn't fail because it was poorly designed. It failed because it succeeded too well. It went faster than planners expected, landed hotter than engineers predicted, and pushed stress into places no one had worried about before. The sky welcomed it. The ground did not. Every cracked runway and glowing brake told the same story. Progress doesn't move at the same speed everywhere. This plane forced engineers to accept something uncomfortable. You can't upgrade one part of reality and expect the rest to instantly catch up. Airports, materials, safety systems, and human reaction time all have limits. And when a machine ignores those limits, the weakest link always reveals itself. In this case, it wasn't the engine or the wing. It was the runway beneath the wheels. Today, many of the lessons from this aircraft still shape modern aviation. Stronger brakes, better tire compounds, smarter landing procedures. Even new airport designs. The plane may no longer dominate the skies, but its influence is everywhere. It quietly changed how engineers think about speed, infrastructure, and balance. That's the real secret of Forbidden Engineering. The most dangerous machines aren't always the ones that explode or crash. Sometimes, they work exactly as intended, and that's the problem. They expose how unprepared the world is to support them. If this story surprised you, drop a comment and tell me which aircraft or machine you think pushed engineering too far. I read every comment, and your ideas often shape future videos. And if you know someone who loves aviation mysteries or extreme technology, share this video with them. It helps the channel reach people who enjoy stories like this. Make sure you subscribe to Forbidden Engineering, because there are many more machines like this, one built to defy limits, and quietly abandoned when the world couldn't keep up. Thanks for watching, and I'll see you in the next story.